There's actually two different types of refractive indexes. The one that we actually went through just now was actually what we call absolute refractive index, which means that we are basing it off against air or vacuum to another medium itself. Because usually when you use the formula C over V itself or sin I over sin R, by right, we are actually comparing it against vacuum. So it's actually usually is vacuum versus medium. However, because of air being almost having the same refractive index as vacuum, sometimes we also mention that it's air instead. So normally the one that we use sin I over sin R or use your Snell's law itself, typically is actually solving for the medium itself. However, there are some cases itself where we have two different mediums of that is not air or vacuum itself. Could be water and glass. So because of this itself, there's a term what we call relative refractive index. So basically, between these two mediums itself, what is the refractive index accordingly? So some schools cover this, some schools don't. Just gonna cover it just as exposure so that everyone knows that at least you know that. Okay, between, for example, water and oil, water and glass, all these different mediums that is not air or vacuum, we are actually looking for, we are actually solving for their relative refractive index itself, where it is just N2 over N1, where N2 typically is the, let me just jot this down, usually this is the optically denser. Because ultimately, don't forget, it is always going to be greater or equals to 1. So remember, the angle on top must always be bigger, and therefore N2 must be bigger than N1 itself. Okay? Otherwise, this thing won't work. But you don't need to worry too much because this one I would say not a lot of schools actually cover this part. Even if they do, they don't really call it relative refractive index. We just call it refractive index itself. Okay, so let's take a look at the work example here. So you have light rays moving from point A to point B. Okay, I think that they just mean that it's passing through itself, and you have a relative refractive index, just have a refractive index of 1.5. Okay, so if you want to find A is actually the angle of refraction after the light ray enters the block, right? So very first thing we can do, we can just write sin I over sin R. Now, this one, same thing, because we're moving from air to acrylic, you can see that the 55 degrees is actually bigger than angle A, right? So what we can do is we can just put in the numbers. This is 1.50, you have your sine 55 degrees, and you have sine A at the bottom. So all you need to do is solve, so that after you shift it over itself, sine A is equals to sine 55 over 1.50. Okay, then if that's the case, all you need to do is take sine inverse of sine 55 over 1.50. Then you take out your calculator and then you press the values accordingly. So sine inverse, since there we put the fraction sign, with sine 55, close the bracket, 1.50, close the big bracket. You end up with 33.100, and you will just round it up to 1 decimal place. Okay, then they want you to solve for the value of theta itself. So to solve for theta itself, because the question asks us to calculate and not directly state, we have to slowly calculate it out. So B and A, they are actually the same value. Okay, because of alternate angles itself. Okay, so because this, we're gonna use the 5SF, not that it makes a big difference, but we're still gonna use it to show the teacher that we know what is the steps itself. We don't use the final answer, we have to use the intermediate step, the 5SF value. Okay, so using the same formula itself, but now do take note, we are moving from acrylic to air. So what we're gonna do is instead we'll put R over I. Okay, so 1.50 is now gonna be sine theta over sine 33.100. Okay, so now we're gonna solve itself. If you just rewrite the formula, you will end up with sine inverse 1.50 times sine of 33.100, close bracket. Okay, so press this, 1.50 times sine 33.100, close bracket, 2 times, and you end up with 55.000, and we can just simply write this as 55 on dp. Okay, so after this, don't forget what is the question asking for. What is the relationship between your incident ray and your emergent ray? The incident ray and the emergent ray are parallel. Okay, not sure if you realize that, but basically they are actually parallel. That's why you can actually state that they are actually same angle. Because if you think about it, this is actually your vertically opposite angles. If, because the normals, they're all straight up vertically, right? And basically if these two are parallel, you will get a vertically opposite angle where the angles are exactly the same. Now next one, for question 2 itself, state and explain which one is higher refractive index. Remember, higher refractive index means you're optically denser. So medium A has a higher refractive index than medium B. Why? When the light ray, so you can see every time we want to explain refraction itself, there's only one explanation or one format. When the light ray travels from medium A to medium B, so just double check, all you can do is take your ruler, 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3. Okay, so you can see, yes indeed, when your light travels from A to B, the light ray speeds up and bends away from the normal. Okay, so this means that medium B is optically less dense than medium A. Okay, so that is why you have a higher or larger refractive index itself. Now, next one, calculate the refractive index for B if A is given to be 1.50. So this one you can actually use the relative refractive index to directly solve itself. It's perfectly fine. However, I wouldn't really suggest that. It will be easier for you to just solve it one by one, but it does take a while more. It does take quite a lengthy explanation. So first things first, this is 40 degrees because of the 90 degrees over here. So you have to solve for A first, then you solve for B, and B you can solve for 30 degrees. And then you can use this to help you solve for the final answer itself. Okay? So let's attempt this. Alright, so first things first, we need to solve for angle A. So what we do first is we use n equals to sine I over sine R. Now why we can use this is because don't forget we are moving from air to A. So we can use this directly. So 1.50 is equals to sine of 40 degrees. Okay, and then we have sine of A that we don't know. So just to solve for A itself, this is equals to your sine 40 degrees, with the brackets, over your 1.50, and we can directly solve. Press the calculator. We will have sine 40 over 1.50, close the bracket, you end up with 25.374 degrees. Now we don't round this up at all because we are using this to solve for later parts. So the first thing next is B is equals to A, so they're both this value, 25.374 degrees. Okay, so we're gonna use B to help us solve for our value itself. Okay, so you can just see from this, you can actually solve. Okay, sorry, I take that back. Basically, we have to use the Snell's law to solve, otherwise this one can't really be solved. So first thing, if you notice at the in-between here, we are traveling from A to B, so I'm going to use A equals to B. Okay, so let's take a look at it. Okay, I think I forgot to take them out. So if I'm not wrong, So sine B is the 25.374 and NB is what we don't know. Okay, let me just write this properly. This should be I, this should be R. So let's throw in the numbers itself, 1.50, and you have sine 25.374. Okay, then equals to n of b, which we don't know, times sine 30 degrees. Okay, so with that we can just solve for b, which is, just press the calculator itself. Fraction first, 1.50 times sine 25.374, close bracket, divided by sine 30 degrees, close your bracket, you get 1.2856. And then we will just run this up to 1.29 3SF. Okay, so that's all for this part. Actually, if you were to know how to draw it itself, or you have actually recognized it, basically, just like the previous question itself, this fella is also 40 degrees because you're now back in air, and these two surfaces itself, they're all horizontal, which means that this light ray and this light ray are actually parallel itself. So if you know that that is parallel using your alternate angles itself, you can actually find 30 and 40 itself, which means you can actually directly solve for B by using sine 40. Remember, we always use big angle over 30 degrees. So this question, very tricky. However, if you were to know the concepts well itself, you can actually directly solve that this is 1.2586, 1.29 3SF directly without doing all these complicated steps itself.